Hey there, Matt Fiske coming at you from my studio at the Red Lodge Clay Center. And I want to show you some images that I took using a scanning electron microscope. For my first image, I think it would be useful to show you what's possible with kind of a basic optical microscope. So if you've ever taken a high school chemistry or science class, you're probably familiar with a microscope. And the way that they work is they reflect light onto a slide or a sample, and then you look through eyepieces and you see the sample or whatever it is you're looking at. And so we had one of these at Utah State, and this image is of a manganese saturate glaze at about 600 magnification. I was playing with these over in geology. I was bringing my glaze samples over, trying to figure out what was going on with the surface features, and I just wasn't getting the resolution that I wanted to. So they told me that I should look into the scanning electron microscope. And what it looks like is this. And so you've basically got three components here. You have the vacuum chamber, which is kind of the larger box, and on top of the vacuum chamber you have the column. And then to the left of that you've got the computer monitor, or the screen, and that's part of the processor. These are four of my ceramic glazes that I prepared for this machine. You might notice that they're all wrapped up in foil, right? And that's because using the electron microscope, you have to kind of operate on a set of rules. And the rules is that the object that you're looking for has to be conductive. And if it's not grounded, then these electrons that you're shooting at the sample will sort of bounce off, and the detectors just won't get the right kinds of information. So I think it would be useful to explain what the information is at the bottom of these images. On the left, we've got HV. That corresponds to the energy of the beam. HFW corresponds to the horizontal field width, and usually those units can be in millimeters or microns. And then we've got magnification, right? And so anytime I look at a scanning electron microscope image, I first look at the magnification, and then I look to the right hand side and I look at the scale bar, right? And so just like a road map, that little bar will give you an idea of the scale. And in this case, it's 50 microns, which is about the diameter of a human hair. The scanning electron microscope will max out at about 300,000 magnification. So you can, in very high resolution, see nanoparticles. So this first image is looking at one of the glazes that I came up with at Utah State. It's a hare's fur oil spot glaze. And to make this image make a little bit more sense, I think it would be useful to explain what an oil spot glaze is. The simplest way to kind of describe that is that you take a glaze and you saturate it with iron oxide. Iron oxide is Fe2O3. So you've got 2 iron molecules and 3 oxygen molecules. Well, if you fire that oxygen molecule, that iron oxide molecule, hot enough, it becomes unstable. And we call that thermal reduction. So it has nothing to do with the atmosphere inside of the kiln, but it has everything to do with the temperature that it's at in the glaze. And once you reach that thermal reduction temperature, the Fe2O3 will split apart and it'll become FeO and FeO, and it'll give up an oxygen molecule. And what that means practically is that the glaze will start boiling. And if you have an iron oxide rich clay body, that will even start boiling. And I'll show you an image of that here in a minute. But you've got this boiling glaze, and then what you do in an oil spot firing is you just continue to fire, and that bubbled, boiled, cratered glaze will eventually heal over. And what you're left with are really high concentrations of metallic oxides on the surface of the glaze, right? And those concentrations look like little droplets, so hence the name, an oil spot glaze. And so in this image, that's exactly what we're looking at. We're looking at an oil spot droplet in the center, and then on the outside, we've got these kind of blown out, washed out white areas. If you've got really good conductivity, you'll get a really good high contrast image. And if you're dealing with something like glass or pure silica, you don't have a lot. So that's why kind of the outside of the image is washed out like that. And so again, this is at the center of an oil drop, an oil spot, and we are at 1,000 magnification. And we're focused on kind of a really dramatic structure. It looks like a mineral sample, right? And it looks an awful lot like hematite or magnetite. And so I took this image over to the geology department and I said, okay, what is this? What's going on here? And I got a really great answer from Jim Evans, who reminded me of the Bowen's reaction series. And when you've got a super saturated solution of rock or minerals, right, everything, when it's really hot, everything is in solution. But as things cool down, your minerals will drop out of the solution and they'll begin to crystallize, right? That's what the Bowen's reaction series is. And so that relates directly to this image because at the very center of our oil spots, right, we've got the highest concentrations of iron and to a lesser extent magnesium and manganese, and some other stuff. You know, we're almost never purely one thing. And so that's what crystallizes first, right? Because it's all right there and it crystallizes very easily. And then as we move out, we start to see a transition into kind of a silica iron hybrid. And then as we move out further, we start to see just the normal black glass, right? A much higher concentration of silica and almost no iron. So that was really, really instructional in me kind of thinking about these glazes because it kind of directly related it back to mineralogy. So here we are at 1,000 magnification. So let's move up where we are at 10,000 magnification. And so I wanted to zoom in on these kind of structures and take a look and see what was happening with the crystallization. And what I learned was that this is almost pure magnetite. And it's just absolutely beautiful. We're moving from our kind of central super saturated concentration of iron, and then we're moving outwards. So what's going on with these iron crystals is that they will actually grow in rows and columns, right? Because as you move away from your highest concentration of iron outwards to lower and lower concentrations of iron, is they'll actually kind of take the path of least resistance. And it's much easier for a crystal to grow on the side of another crystal than it is for a crystal to kind of grow all by itself in the middle. And so that's what is going on with all these branch-like structures. The iron is falling out of solution and it's crystallizing in the easiest place that it can. And then on the right-hand side of the image, you start to transition from a solution of really ready iron into a solution that has a lot less iron and a lot more silica. So then the dynamic starts to change. And if we go back to our bones reaction series, that would be kind of like the next level, or kind of the next step down. So once all the iron is exhausted, you transition into iron silicate. And then once all the iron silicates are exhausted, then you kind of move into the next stage, which is almost pure silica glass. With the samples that I was using, initially I had no idea what I was doing, and so I was just taking over broken chunks of glaze because we were really worried that having too much clay, and too much porous clay to be specific, inside of the vacuum chamber was going to cause problems with pressurization. But we just decided to try it anyway. And so one of the kind of happy accidents of using those broken samples was that I was able to get some really fantastic cross sections of glazes. What we're looking at is actually a broken edge of a glaze. And on the right side of the image we have the surface, and then moving left we can actually see the thickness of the glaze. And this is a really interesting image in that we can see a bubble that has been kind of frozen in the middle of that glaze. And then on the bottom section, we can actually see these iron molecules as they were coalescing inside of that glaze bubble, right? So this is like an oil spot droplet forming in the middle of the glaze, just frozen in time. And then as we move to the left, we can see the stoneware clay body itself. And as I said, if you have a clay body that is really high in iron and you're firing an oxidation, your clay body will actually start boiling and bubbling. And on kind of the human scale, you can't tell that, but at the nanoscale, you certainly can. So the next image I want to talk about is a different type of glaze, and it is this glaze right here. This is another oil spot glaze, and this is what I call the lava oil spot. And it is made from two volcanic rocks. This is a rhyolite, and this is a lava rock, right? Basalt. And this one is really interesting. I didn't have a whole lot of time to research this glaze, but when we got up past 1,000 magnification, we found fields and fields and fields of these really interesting crystals. Essentially what we've got are iron silicate crystals growing out of these central little points. And what I speculate is that the rhyolite that I'm using has tiny pieces of topaz, and this one actually has, this sample actually has a lot bigger pieces of topaz. But what I'm speculating with this image is that as I'm ball milling my rocks to produce the glaze materials, the rhyolite itself is ball milling and weathering down and getting really fine, but the topaz crystals are basically resisting the weathering and resisting the ball milling, and they are then acting as little alumina seeds for these crystals to grow out of. And here's another image at 5,000 magnification. And I wanted to show this because this kind of central structure, this big white dot right in the center, is, believe it or not, a piece of kiln wash. So anytime you are kiln shelf grinding, this is what the dust that you kick up looks like at 5,000 magnification. We've got these really large crystals, iron silicate crystals, growing from these kind of central seeds. The third set of glazes that I looked at was a manganese saturate glaze. And so this is an example. The surface is iridescent in some cases, but in other cases it is kind of a really matte, kind of gunmetal surface, almost like graphite. And I've been interested in manganese glazes, trying to understand why certain glazes have iridescence and others don't. So I took one of my manganese glazes over, and this is what it looks like. And this image is really interesting because, like the Stoneware oil spot, you can actually see the surface of the glaze, and then you can see the thickness of the glaze. And then on the bottom left, you can actually see the porcelain. And essentially what the biggest difference is that porcelain is much higher in silica. And so you've got a much glassier clay body. This image is at 50 magnification, and you can see our scale on the bottom right is 1 millimeter. And this is actually the copper tape that is holding the sample down and grounding it so that we could get really high resolution. Let's zoom in on the small little window, and this is 3200 magnification. So these tiny little flower looking structures are kind of really unique to manganese and the way that manganese crystallizes. And in particular, when manganese crystallizes, in some cases, it will be really iridescent, right? So you'll get this kind of rainbow surface. And all the most rainbow, the most iridescent surfaces, all have this kind of structure. And then here we are at 25,000 magnification. And at this scale, we're at 2 microns. We are looking at nanoparticles of manganite, which is iron manganese mineral. So before I go, I just wanted to share with you some of my books, and this is my go-to. Anytime somebody asks me where to get started, this is where I got started. This was the first book I ever bought as an aspiring potter, and it's John Britt's book. It's the complete guide to high fire glazes. And with my oil spot research, I started right here on page 76 with some recipes for oil spot glazes. And this book is really great because it'll even give you an idea of the materials themselves. So that's kind of the number one place to start. My other very early editions, Robin Hopper, the Ceramic Spectrum, and then Daniel Rhodes, Clay and Glazes for the Potter. Excellent, excellent books on glazes. More technical, Hamer and Hamer, the Potter's Dictionary. This is a great book to have in the studio. If you ever get a chance to attend a Bill Carty workshop, he is an unbelievable mind in terms of exactly what I've been talking about. He does workshops for potters, ceramic science for the artist. So check that out for sure if you're ever in the area where he's giving a workshop try and make it. This is a really cool book. It's called Minerals of the World. Spring Books. It's full of a ton of really beautiful pictures. All the minerals, all of the chemical formulas. In terms of inspiration for work, like this is a really great kind of book to page through. Another useful book to have if you're into minerals is the National Audubon Society Field Guide to Rocks and Minerals. This is like the best of the best in terms of identifying what's going on with what you're looking at. Thanks for joining me, and have a great clay week. Bye-bye.